Hi students, it's Dr. Marks, and our topic for today is presenting regression results and discussing with precision. So what I mean is being accurate in the things that you're saying when you're discussing your regression results. So as I said, we're going to discuss how to present your regression results, but my goal here is to get you prepared for data analysis number 3. I want to see everyone get a great score on that. And this includes crafting appropriate tables, discussing your t-tests, using the critical T, but doing so efficiently so you're not saying the same thing over and over again. We're going to talk about scaling results when maybe they're so small that you need to make them more meaningful. I'll give you an example. And language that is required for us to be precise, but also accurate. This is important not just for data analysis number 3, but if you're writing for other professionals. And I've actually had students leave this class and do regression work for their bosses and really impress their bosses. You don't have to have a super sophisticated model to get some interesting conclusions that might help you in your job. So think of this as technical writing when you're presenting regression results, kind of some do's and some don'ts, a whole lot more do's than don'ts. And I'll also be offering you some very important reminders. Now, let's start by talking about the hypotheses, because in your regression model, you have multiple explanatory variables, right? We're probably not looking at just one explanatory variable. That means your software that you're using, whether it's Excel or R or Stata or SPSS, is estimating multiple coefficients at one time, and your results are going to give those to you. So you have a model with, let's say, 4 explanatory variables or maybe more. So you have a beta 1 and a beta 2 and a beta 3 and a beta 4, and they're all coming back from, in our case, Excel in one table. So when you're crafting hypotheses, any hypotheses must match this notation so that the reader understands which coefficient that you're talking about. If you simply craft a hypothesis that says your alternative hypothesis is that beta is greater than 0, well, that's kind of unclear because you're estimating a whole series of betas, but they needed to be named beta 1, beta 2, beta 3, beta 4, or something like that in your model, or beta, alpha, gamma, doesn't matter, but the notation needs to match. What does make sense is having an alternate hypothesis, beta 2 is greater than 0, because beta 2 is tied to whatever variable is next to it in the model. That makes it much more precise. So this is important to do. If you're crafting any hypothesis, please make sure if you're also giving an equation that they match. Let's talk about tables. Tables are key to presenting your regression results, because obviously with multiple regression, there's a lot of parameters that are being estimated. You're getting a whole lot of information back. You've got your coefficients, you've got your t-statistics, your p-values, lots of information. Plus, there's information about your sample size and degrees of freedom. That kind of information all needs to be presented in your tables. So here are the key things that have to be included in your tables of regression results. Obviously, you need to have your list of explanatory variables using the variable names so that they match everything else that you've been saying. You're going to have your coefficients, right? Remember, these are the estimates of your betas, your parameters. Your standard errors, will remind ourselves what a standard error is in a minute. T-statistics, your p-values, the number of observations, your R-squared, and your adjusted R-squared. These are all things that need to be there. And then finally, you need to add to that a legend for indicating significance, and that's using an asterisk method. This is pretty common across disciplines, so I'll show you that as well. This does mean that you might have to craft your own tables that Excel may not give you exactly what you need in the format that you need it. Here's an example, and I just pulled this out from a paper that I worked on with a student. So, and you see in the first column, we've got our variable names. Probably I've given you variable names and I've asked you to use those variable names. All right, remember these are just your explanatory variables. These are all those things that have an impact or turn out to not have an impact on your dependent variable. Then we've got our coefficients, right? These are those estimates, the parameters. So this tells us the magnitude of the effect. Notice some are positive, some are negative. So that tells us if they would have an increase in terms of its effect on the dependent variable or if they would make it decrease. But that by itself doesn't tell us everything because it doesn't tell us anything about significance. Now we've got our standard error report. Now, standard error I know is kind of an abstract concept, so I've given you a reminder to the right. The term standard error is used to refer to the standard deviation of various sample statistics, such as the mean. So we did some examples earlier units about how we would get a standard error. But basically, the standard error, and again we abbreviate it with SE, is the approximate standard deviation of a statistical sample population. If you look below, I'm showing you the statistic for how it's calculated. So standard error takes the population standard deviation, divides it by the square root of the sample size. So it's adjusted for sample size. All right, next, we've got the t-statistic. So if you recall in the lectures, we've got the hurdle and the hurdler, right? The t-statistic is the thing generated by our program. That is the hurdler, the thing we're trying to see if it exceeds the hurdle, right? The critical t. We'll talk about those asterisks that I'm using in just a second. And then we've got the p-values. Remember, p-value captures the probability of a type 1 error. In other words, we're asking what is the chance that we reject the null hypothesis, in this case that our coefficient is really 0, when it's actually true? What's the chance we've rejected the null hypothesis when we really shouldn't have, given the data? In this case, it's really getting a sense of what's the probability that we've gotten this wrong. Remember, smaller is better. All right. Next thing we see in the table, somewhere you need to report your number of observations. And again, your package is going to give this back to you. Your R square, you see my R square here is 0.658, pretty good. Then the adjusted R square, it's going to be similar to R square, so you've reviewed this already. We know that we're controlling for a number of explanatory variables, so 0.647 is the adjusted R square. That needs to be reported somewhere. Finally, you need to have some kind of indication so that a reader can quickly eyeball where the significant results are. This is the standard, guys. We use 3 stars for saying something is significant at the 0.01 level, so we're 99% confident. We use 2 stars to say it's significant at the 0.05 level, so we're 95% confident. And 1 star tells us it's a marginal result. It's significant at the 0.10 level. Now, we haven't talked about significance at the 90% level much. We have mentioned it in a few places, but I do want you to indicate that. That would not be a very strong result. But if you had the right sign and it's significant at 90%, it's worth pointing out, but you need to acknowledge it's not a very strong result. Now, it's also possible that some papers you might read in the future will have a 4th category, some other kind of symbol. They don't use 4 asterisks just because that gets a little unwieldy, but some kind of other symbol to indicate significant at more than 99%. So we've got everything here. As my note on the right says, look, there's some redundancy in this table. And this was work I did with a student. If I'm writing for my peers, then I might leave out the p-values because the asterisks basically do the job of the p-values, but having them both isn't a problem. No one's going to look at you and go, ugh, this person doesn't know what they're doing. For our purposes for this class, since we want you to be thorough, for purposes of illustrating your understanding, you're going to include both. But I do acknowledge that there's some redundancy built in here, but keep in mind, you are illustrating to us that you understand all of this stuff. All right, let's move on. Now, you might decide that you want a table that looks at 2 different models side by side, and that is fine. You can do this in different ways. I'm showing you one way in case you feel like you're running out of room. So if you look here, I've got model 1A and model 1B. It's not uncommon to put your standard errors under your coefficients. So what I'm doing there is presenting coefficients, and if you look at natural log of undergraduate enrollment, the very second one, you see a different symbol. So here we're using hashtag for this paper that I worked on with Professor Zirkle to indicate a p-value of 0.001, 99.9% confident. Model 1B does the same thing, but notice what I'm doing here. I am adding some variables. Pretend that columns 3 and 5 are filled in. I'm just showing this as a potential way of doing it. You can design your tables differently. Just be sure that it does cover all of the things that needs to be in here. These dashes here are basically saying that Model 1A does not include these 3 variables. These are interaction variables. Don't worry about how they work. That's a little more sophisticated. We didn't do any of these, but then you see they've been added to Model 1B. So this is one way. You might decide you want to have more columns. There probably would have been spaces for 2 more columns. And guys, it's okay for you to change the font of your tables to 10-point font. That's generally pretty acceptable. So if you're finding that the tables are a little tight, you need a little more space, make them 10-point, but do make them attractive, make them easy to read. I personally like filling in the rows with shading every other one just because it's easier to eyeball, but you can decide how you want to design your tables. All right, so we've gotten through hypotheses that need to match in terms of notation in relation to your betas. We've talked about crafting your tables, understanding that we are going to err on the side of being more thorough. We're going to have our asterisk coding, and we're going to have our p-values. Please make sure that all of those things that I said needed to be in your tables is there. Now, let's talk about how to efficiently present our results so you don't feel like you're saying the same thing over and over and over again. Now, again, this is for purpose of illustrating your mastery of topics because this is a class, and while we want you to have good professional writing techniques, we do ultimately need you to show mastery. So you must discuss p-values and show t-tests, all right? Make sure you understand that. Now that means you're going to have to look up the t-critical for the appropriate level of confidence using a t-table. That's probably not being given to you in your results from your regression, but we know how to do that because we've done that over and over and over again in lecture. This can take up a lot of room and get really redundant, right? Because your critical t is going to be the same for each of your variables. If you're looking at 95% confidence, the t-critical is the same. If you're looking at 99% level of confidence, the t-critical is the same, right? So you might feel like you're saying the same thing over and over again. So here is a suggestion for being efficient, and I would like you to follow this model in your report for 2 reasons. One, completeness. It'll make sure that you have done what you need to do, but also ease of grading. Now, what I don't want you to do is literally take this language so that everyone has the exact same language, but you get the idea. However, again, I just want to remind you that I'm not likely to do this, and you're probably not likely to be redundant in this manner. If you're writing for your PhD economist boss, clearly he doesn't need both of these, but remember this is a class. We are illustrating mastery of topics. All right. So here's my suggestion for how you put this information together very quickly. So here I'm talking about a result that's significant. I'm indicating my p-value 0.0062, clearly significant result. I've given you my t-statistic. T is 6.15. It's greater than the critical T of 2.33. And I'm doing that for all of my significant variables, right? This is pretty efficient. You don't have to say the same thing over and over and over again. Please give me this kind of information so that we can kind of check you off as having done this and showing that your test passes the t-test, right? Let's move on to talk about interpreting results. This is where a lot of students lose points because they'll say, oh, this is significant, but then they don't go on to interpret, and you must interpret. So let's look at my language here. I say 2 of the variables related to the racial composition of each district, this was a voting study, were found to be significant at the 99% level of confidence and had a positive impact on voter turnout. So this is a paper explaining voter turnout across different precincts. And we concluded a 10% increase in the proportion of population that is white raises voter participation by 2.7%. And again, I'm showing you that it's significant with my p-value and my t-test. And then I go on to say that a 10% increase in the proportion of the population that is black increases participation by 2.3%. So let me please warn you that if all you do is say this variable is significant, you have not done your full job, because your job interpreting regression is to tell us what variables are significant, right? What variables are significant, and then you need to tell us the impact and what it means. Tell us what those coefficients tell us about the impact of that significant variable on your dependent variable. So we are going to be looking for this. One other thing I want to remind you of is that you need to be using the phrase holding all else constant. That is important. Holding all else constant reminds the reader that when I tell you that a 10% increase in the proportion of the population that is white raises voter participation by 2.7%, and that when we have a 10% increase in the proportion of the population that's black, that increases participation by 2.3%, that these are just not comparisons of means like we did with hypothesis tests. This is controlling for all the other confounding factors, right? That's the beauty of regression. So that's why we say holding all else constant. Now, do you need to say it in every single sentence? No, but you need to kind of be clear that when I discuss this result, it's all else constant. So notice I've kind of combined two different results, holding all else constant. Or you can say all else constant. Both are okay. The next thing related to having good interpretations of your coefficients for those significant variables, you need to be clear about units. This is very important. So be specific about what units are being measured. Be precise. It's important to remember that a coefficient, those betas, they're measuring the impact on the dependent variable of a 1 unit change in an explanatory variable. In other words, when your explanatory variable changes by 1 unit, how does that impact your dependent variable? Does it make it go up? Does it make it go down? If so, by how much? Again, for significant results. But here's the thing, what is a unit? You can't just say a 1 unit change, you need to be specific about what a unit is. Be clear. A unit could be money, it could be measured in years, a unit could be a percentage, so your language needs to be precise. For example, maybe you're looking at what is the impact on crime rates, your dependent variable, in county X when percent male increases by 1%. Well, what this tells me is you have a dependent variable, crime rates, and percent male is your explanatory variable. So a 1 unit change in that variable, percent male, is a percent, 1%. So you need to be very clear. When the percentage of males changes by 1%, not 1 unit, say 1%, then crime rates do this. They either go up by this amount, down by this amount, whatever your result is. Another example, what's the impact on bone density in women when age increases? All right, so bone density in women's my dependent variable. Age is one of my explanatory variables. What's a unit change? A 1 unit change is 1 year. So you wouldn't say when women's age changes by 1 unit. You would say when women's age changes by 1 year, all else constant, the impact on bone density is blah, 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 blah. Be clear about what constitutes a unit. All right, so going back to the example I just gave you, a 10% increase in the proportion of the population that is white. So I'm not saying a 1 unit increase or a 10 unit increase. I've scaled this here. I'll tell you why in a minute. But I'm being very specific. A 10% increase. So if you're working with dollars, a $1 increase, or you might change it to a $1,000 increase, but use the units. This is important. What if you get an unexpected sign for a significant result? Now, keep in mind, it's important. We're talking about significant results. If they're unexpected signs for insignificant results, we don't care about that so much, right? So suppose you get a result that is the opposite of what you expected in a one-tailed test. So maybe you have a variable, x1, its coefficients being estimated with beta 1, and your alternate hypothesis is that beta 1 is greater than 0. In other words, you think beta 1 will cause your dependent variable to increase. But then you get your Excel output, and the estimate you get for beta 1 is negative 2.34. And you're like, wait, negative? And it's significant at 95%. Remember, if it's not significant, it doesn't really matter. But if it's significant, then the data is telling you, for whatever reason, what you're working with, the data you have, and the model as you've specified it, has this counterintuitive result. So what do you do here? Because this violates your hypothesis, right? In this case, technically, we would fail to reject the null hypothesis, but that's not exactly how we do it in regression. Here, we just have a counterintuitive result, but it's still a result. It's statistically significant. So maybe your hypothesis was wrong, but we need to acknowledge this. It's important for you to point this out. So let me give you an example here. And also let me point out, before I give you that example, that if you had something like this could be a sign of a specification problem. So if you really think that beta 1 should be positive, especially if theory suggests beta 1 should be positive, or just common sense suggests beta 1 should be positive, this would be your kind of red flag that, okay, there's something going on here. Maybe you've got an omitted variable, maybe you've got variables that are too closely correlated to variables in your model and they're causing problems with each other. This would be your signal that you want to take a little closer look. All right, so in the paper that I wrote on voter turnout with this student, we said, median income. We had this weird sign on median income. So we discussed the results, but we acknowledged, as you see right there in that red box, median income had an unexpected sign. So I want the reader to understand that, I get that that's kind of a strange result. It's important for you to point out where things are counterintuitive. But again, remember, this only makes sense if we're talking about a significant result, right? If it's an insignificant result, then we're basically saying that it doesn't have any explanatory power. So it doesn't make sense to point out a wrong sign if it's an insignificant result. So keep it simple. We're talking about our significant results. Let's talk about scaling. Sometimes we need to scale our significant results so that the results are framed in a more meaningful way. I'll give you an example and that will make more sense. But remember again that coefficients measure the effect on your dependent variable of a 1 unit change in your explanatory variable. But what if 1 unit is really, really small, and maybe 1 unit change in your explanatory variable is so small that it's going to estimate a coefficient, but that coefficient is going to be super, super, super tiny. And if so, it's not really meaningful. So here's what I mean by that. Let's say that we're looking at percent of women completing high school across countries. Percent of women completing high school. So that's our dependent variable. And we think that this is a function of GDP per capita. If you don't know what GDP per capita is, for those of you that haven't had econ, don't worry about it. It's just a proxy for average income. So GDP per capita in the United States is, I haven't looked it up for a while, but it's probably in the $70-something thousand, right? So think about this column of data would be kind of the average household income measured in many, many thousands of dollars. In some countries, obviously a lot smaller. Could be $12,000 if we're talking about, let's say, Thailand. Remember again that our coefficients give us the impact of a $1 change. So this is a $1 change in GDP per capita. So think for a second. Is it likely that a $1 change in average income is going to have a meaningful impact on completion of high school? No, because that $1 change is just too small. It's just not meaningful. The impact of the $1 change might have an impact, but it's going to be so tiny, 0.000 something maybe, the coefficient is essentially 0. So it might make sense to scale all of this information in our discussion. So what do I mean by scaling? All right, let's suppose that we got back a coefficient of 0.00012 as being the impact of a $1 change on percent of women completing high school. Everyone agreed that's essentially 0, which makes sense, right? A $1 change is negligible. But a $1,000 change in GDP per capita, that's not so negligible. So I might choose to scale the 10,000 change in GDP per capita. And for a $1,000 change in GDP per capita, now what I do is I've got to take the coefficient, multiply it by 1,000 times, because remember 0.00012 is for $1, but we're doing $1,000. Now I've got 0.12%, and that's not negligible. I mean, it's not huge, but it's not negligible. So the percent of women completing high school increased by 0.12%, all else constant, for a $1,000 change in GDP per capita. That's where scaling helps us. But please, for purposes of grading, so that your coaches can follow your work, please explain a 1-unit change so that they can see that you've got that right. And then you can go on to say, but look, if we scale this to a magnitude more reasonable, now we have something that is more meaningful. We've been talking about explaining significant results, but let's turn our attention for just a second to what happens when it's time to discuss insignificant results. Well, I'm pointing this out because this is often where people go wrong in these projects. If something is statistically insignificant, remember what that means. We fail to reject the null hypothesis, right? We fail to reject the null hypothesis. So what we're saying is that we cannot reject that beta 1, beta 2, whichever beta we're looking at, is equal to 0, right? So if we can't reject that beta is equal to 0, then we're saying, look, that coefficient might, for all practical purposes, be equal to 0. Doesn't matter what Excel reported in the coefficients. The fact that it's statistically insignificant means it's not statistically different from 0. So we cannot claim that the coefficient, which again measures the impact on the dependent variable, is anything other than 0. So where do I see people going wrong here? Well, they jump to the coefficient and go, oh, the coefficient is 5.23, and they start interpreting it. And then they say, oh, but it's insignificant. Well, that doesn't really make sense. If it's statistically insignificant, then that coefficient isn't different from 0. And that's really what you need to say, that it does not have an impact. This explanatory variable does not have an impact on your dependent variable. We cannot claim that the coefficient is any different from 0. Let's move on to some reminders, and these reminders are going to start with reminders about interpreting your dummy variables. This is another area where people struggle. Now, remember guys that simple dummy variables have an omitted category, and I urge you to make sure you've gone back and reviewed the stuff on dummy variables that I've posted for you. A simple dummy, 2 categories, it's binary, married versus not married. That would be a simple dummy variable. But we don't need or want both in the regression. The reason we don't need or want both in the regression, it's going to cause an error. The reason it's going to cause an error is because they're perfectly correlated, right? One is a perfect predictor of the other. If you are married, then we know we can predict exactly what you're going to have in the column for not married, 0. If it's a 1, then we know the other column is a 0. One is a perfect predictor for the other. It's perfectly correlated. Any of your regression packages is going to have a problem. So that's why we coded only one of them. We might have had gender where we had male and female, and we had to pick one or the other. In this case, we have to pick married or not married. So let's say in this case, we have married equals 1, 0 otherwise. That's all we need. We don't want to use both in our models. Interpreting this is important. This means our coefficient, when we put married in our model, tells us the impact on our dependent variable of being married, but this is the key part, relative to the omitted category. Our omitted category is being not married. So it tells you the effect of being married on your dependent variable relative to not being married. So let's look at an example. Let's say we're explaining people's weight. And those of us that are married and cook for our spouses or sit down and eat with our spouses probably think that it matters if you're married or not married. So we're going to have a dependent variable of weight, and we think it matters if you're married or not married. And let's say that we find our variable, married, is statistically significant and positive. So if married is statistically significant and positive, think about what that tells us. That tells us that someone who is married has a higher weight, all else constant, than somebody who is not married. In other words, if we were comparing 2 groups of people that only differed in the only way of being married versus not married, that's the holding all else constant part, we're saying that the married people weigh more. But you've got to be precise in your language. Someone that is married has a higher weight, all else constant, relative to somebody who is not married. So be precise in your language. We're always interpreting our dummy variables relative to the omitted category. Let's review how to discuss categorical variables, because again, this is where we see a lot of errors. Let's say that we're looking at grade point averages and we think it matters what class you are in as an undergraduate. So we're going to have 4 categories: freshman, sophomore, junior, and senior. And we need an omitted category. And by the way, if you're ever doing this kind of work, I've given you which category to omit, but if you had to pick your own, it's usually best to have, if something is orderable, like in this case, freshman is younger than sophomore, younger than junior, which is younger than senior, use the first or the last category. It makes interpretation a little cleaner. So we need an omitted category. I'm going to pick seniors. So the coefficient on freshmen, when we put freshman in our model, and be clear, freshman, sophomore, junior appear in our model, senior is our baseline. The coefficient on freshmen tells us the impact of being a freshman relative to being a senior. That's key. Relative to being a senior, because seniors are our omitted baseline category. Let's say that we run our model, we get a negative and significant result, negative 0.54. That's what we get back for freshmen. What that tells us is being a freshman lowers GPA by 0.4 compared to being a senior. That part is crucial. Compared to being a senior, all else constant. So guys, in your interpretations, it's crucial that you're interpreting your dummy variables and categorical dummies relative to the omitted categories. And if you don't do that, you're not going to end up with good grades on these portions of the project. So please make sure you're being precise. Let's talk about converting p-values and when you might need to do that. It's important to remember that p-values assume a two-tailed test. So be clear, we've talked about this, when you get your results back from Excel, you are getting p-values reflecting the assumption that you are interested in a two-tailed test. But sometimes we have one-tailed hypotheses, right? And we've worked with one-tailed hypotheses. Well, in this case, the p-value is not quite right. Remember, though, that the bar is lower for a one-tailed test. That hurdler has a lower hurdle to jump over, right? It's easier, in other words, to pass that test. But the sign has to be right for the one-tailed test. And that makes it consistent with your hypothesis. So if you're working with one-tailed hypothesis tests, you're going to need to convert your p-values. To convert your p-values, you simply divide in half. If the p is 0.08 in your Excel regression, again, that's for a two-tailed test. Then for the one-tailed test, it's just a p-value of 0.04. So look at that. For a two-tailed test, something might not have been significant at the 95% level, but for the one-tailed test, it is significant at the 95% level. Remember, the bar is lower. And this makes sense, right? Since the one-tailed hurdle is easier to clear, we're more confident in getting over it. So the probability that we think we've made an error or we missed it goes down because it's easier to clear. But again, you have to think carefully about what results it is that you need to present. Sometimes we see studies running only two-tailed tests, and it's important for you to understand whether that's okay. It all comes down to remembering that a two-tailed tests have a higher bar. In other words, it's harder to clear the hurdle. It's a more robust test in this sense. So for this reason, it makes sense that researchers might often use only two-tailed tests. They're basically limiting themselves to the harder test. But they do need to acknowledge if signs for their hypothesis, right, the ones that are on their coefficients, are correct, because a two-tailed test, remember, looks at is something equal to 0, not equal to 0. It's not looking at whether you've gotten the sign right, but it is a more rigorous test. So be clear on what you're being asked to do. Understand whether it's okay for the purpose of your assignments to only run all two-tailed tests. It might be, or you might be told not to do that. Depending on the instructions for data analysis number 3, there might be things in this lecture that don't apply. So be clear on what you've been asked to do in that assignment. Regardless, much of these reminders do apply here. It's important that you remember to be precise in your language, especially with respect to dummy and categorical variables. Show mastery of topics. And of course, let me know if you have any questions as you start working on your projects.